Yes, I'm Sean Nardell. Where is she? There's Astrid. I was a grad student of Astrid's years ago. Some of you are very good about telling your years. Let's just say it has been a while. And so I'm very excited to be here and to have all these wonderful people come and talk. So first off is Dave McDonald, who I think, Dave, where's Dave? Dave, you start the Arizona years, don't you?
I do.
Cool. So Dave McDonald's going to talk about the orderly universe of dominance hierarchies as social networks.
I don't mean bad things. No, yeah.
Oh, he's good. Cool. So I'm going to stand up with 2 minutes left, and I'll have a big timer if you need it.
Thank you, Sean. An aged man is but a paltry thing, a tattered coat upon a stick, unless soul clap its hands and sing, and louder sing for every tatter in its mortal dress. Nor is there singing school, but studying monuments of its own magnificence. And so I have sailed the seas and come to the holy city of Albuquerque, I guess. But wait, this is not my beautiful house. This is not my beautiful wife.
Guess I'll have to break the news that I got no mind to lose. Now I guess I'll have to tell you that I got no sentimental. Gonna get my PhD.
Okay, so that was Arizona. Brilliant people have tried to figure out how animals get to the top, including this guy. I'm still thinking, how did that meteoric rise occur? And it's not that easy.
I tell you folks, it's harder than it looks. It's a long way to the top if you wanna rock and roll.
Luckily, I have modeled his rise. This is the last equation in the talk, and I think we can explain it as follows. So, dominance is actually a learned relation. The subordinate, interestingly, we call it dominance, but the subordinate has to accept that subordinate role. It has to sort of give up. And what I want to talk about today is understanding the various costs and benefits of dominance behavior and dominance in different taxa. I think we need a flexible, robust toolbox that can help us work with understanding dominance processes. And I think recently I've gotten into the idea that social networks might be just that. So it's a rigorous quantitative tool for assessing, and I'm particularly going to focus on whether dominance hierarchies tend to be orderly today. So my 3 things will be random networks as a null model expectation for what we might expect to observe. And random networks go way back in network theory, all the way back to Erdos. People have their Erdos number. How far removed are they from Erdos? As far as I can figure out, my Erdos number is about 25 million. But you might be more familiar with the idea of 6 degrees of separation. I'm only 6 degrees separated from Kevin Bacon or some other well-known person, or 2 to 3 degrees from Jim Brown, 1 degree from Astrid, my mom. So random networks is a null model expectation. Second, assessing orderliness via a measure called transitivity, using something called the triad census, not the current measure, which is an estimate of linearity, but which we think, my collaborator Dai Shizuka and I think has some dangerous problems. And third, I'll in particular focus on some data sets using the triad census. This is a social network technique tool, and I'll show some ways of doing that. And the take-home messages will be, one, just the idea that social networks are a useful perspective for looking at dominance hierarchies, and second, that the world is actually pretty orderly. The dominance maybe is a little more orderly than we might at first glance think. So random networks as null models. The random expectation, if you build a random network, the expectation is that 75% of the relations in the network will be transitive or orderly or linear. Okay, you can do this with networks that are 1 million nodes, and you can replicate it 25,000 times, and that's what you'll get out of it. I'm going to show it in a cartoon form, but that is the expectation. So I'm going to show it in a cartoon form with the simplest multiplayer network, 3 players. We have A, B, and C, and we're going to let A dominate B. Okay? Once that happens, there's only 4 possible outcomes. And as I say, this is just a cartoon, but it works for much larger networks. So there are 4 possible non-isomorphic triangles that can occur once A beats B. 3 of those are transitive. They're orderly with a clear top, middle, and bottom. And only one of them is a cycle. So 75% of the possible outcomes are transitive, and only one is a cycle, or a disorderly sort of system. Okay, and that's a general property of random networks. However, observed empirical dominance data sets viewed as networks are much more orderly than that random expectation. I'm just going to show you this one as an example. These are baboon data with 10 nodes as a network. They're the animals, the individual baboons. And the pointy arrows are pointing from dominant to subordinate. And what we see, if we look at it as a matrix, you can actually see where the disorder is. These are low-ranking animals that dominate higher-ranking animals. And you can see most of the numbers are above the diagonal in blue, orderly. There's only 2 below the diagonal, disorderly. Here's a random network with the same number of nodes, the same number of arrows, the same number of dominance relations. And what we see is a lot more disorder. There are a lot more reversals there. So that's, again, a sort of cartoon of what we get. And one of the points is, note the increased number of reversals. Second point is, note that in doing this, comparing the observed network to the random network, we're not messing with the observed matrix. I'm going to talk about that because of this randomization in estimating linearity. All right, so how linear are dominance hierarchies? They're often pretty linear, pretty orderly. They also tend to be sparse. There are a lot of zeros in the matrix. There are a lot of missing interactions. And I don't have time to go into that, but one of the interesting things about that is that those missing interactions may not be just because you didn't do long enough study, but because animals actively avoid each other for very good reasons. Now remember that the random network expectation is 25% intransitivity. 25% of the relations will be cyclical or disorderly. When Dai Shizuka and I looked at 101 published dominance data sets, none of those had a percentage of intransitivity as high as 25%. Usually they were less than 15%, and many of the dominance data sets had 0 intransitivity. There were no cycles in the data set at all. However, the current method, the main method for estimating how linear a dominance hierarchy is by a guy named De Vries, and for arcane reasons that I don't have time to go into, the zeros in the matrix are intractable. And so the method for estimating linearity randomly imputes those missing interactions one way or the other to get at the estimating the linearity. But if you put random arcs in, you know that you're going to get 25% intransitive cycles. So we would argue that you do not want to mess with the observed by randomly imputing, because you're going to put in disorder that isn't there. And along with Trent Reznor, we would argue you do not want to do that. You don't want to impute and put in randomness. All right, that might be the end of the bad music. There's some good music still to come. So one of the things we would argue is if you look at transitivity, what I'll show with the triad census, dominance hierarchies may actually be more orderly than was heretofore appreciated using this linearity method. So I'm going to use the triad census, which is a tool in the social network analysis toolbox for comparative analysis of orderliness. So a network with n nodes, 25 baboons, 32 elephants, has n choose 3 triads possible, ABC, ABD, ABE, ABF, etc. Combinations of n animals taken 3 at a time. So a 10 animal network has 125 triadic combinations, 11 animals, 165, etc. But whatever the number, 536 or 1,000, you can divide those triads into 7 types, okay? So those n choose 3 triads are distributed across 7 distinct non-isomorphic types, and I'll show you those types. The first 2 are pretty simple. We'll just again go back to ABC, 3 animals, none of which interact. That's called a null triad. A dominates B. That's called a single edge triad. Those aren't that exciting. The 2-edge and 3-edge triads are more interesting. So if one animal dominates 2 others, but those 2 don't have an established relation, that's called a double dominant. If an animal is dominated by 2 others, but those 2 don't have a relation, that's called a double loser. Now those 2 kinds of 2-edge triads are inherently transitive. They have to go to this orderly transitive triangle, whichever way the 3rd arrow comes in. So look at it for double dominant, that's a transitive triangle, that's a transitive triangle. Similarly for double loser, that way or that way, it's transitive. So these ones are inherently orderly, transitive, linear, clear top, middle, and bottom, no matter what happens if we fill in those zeros. In contrast, this other 2-edge triad type is interesting because it can go either way. Here A dominates B, B dominates C, and now we want to see what happens between A and C. If the arrow goes that way, it's a transitive triad. If the arrow goes the other way, however, it becomes a cycle. A dominates B, B dominates C, C dominates A, round and round. Who's on top? I don't know. But that's the only way we can get from a 2-edge triad to a 3-edge, disorderly, intransitive, nonlinear cycle. Okay, so those cycles are disorderly. There's no clear top. Okay, so I'm going to look at observed networks. I'm just going to show you a few of them, but I've done this with about 100 data sets. I take the observed network and then compare it to an expected network, which is a random network. Okay, so I have 101 published dominance data sets, generate 10,000 random networks for each, corresponding to each observed network. And the constraint is it has to have the same number of nodes and edges because there's size effects in networks. And for each observed and random replicate, the observed versus the first of the replicates, observed versus the second of the random replicates, we calculate the percent difference of how many of the different types, those 7 types, null, single edge, double dominant, double subordinate, pass along, transitive, and cycle. What's the difference between the observed and the expected? And so we're going to do that. Here's a bunch of data sets. And what we're going to have always along, you can't read any of it, so I'll just sort of point at some of the things. We have the 7 types. These are the cartoons for those little 7 types from null edge. Here's cycles, here's transitives. The 7 types across the x-axis, and then the difference over the 10,000 random replicates between the random and the observed. And really all you need to know is if it's above the line, if the dots are above the little horizontal lines, above the dots, that means that the observed network has an excess of that type of triad. And the little error bars, if they don't come down to the 0 line here, then there's a significant excess. If they don't go up to the 0 line, then there's a significant deficit. And this is a smattering of the data sets. Caribou, macaques, feral cats, dogfish, feral dogs, baboons, ponies, rhesus monkeys, spotted hyenas, mountain goats, pheasants. I read that once as mountain gnats, but I don't know what mountain gnats would do. But pheasants, ants, You might look at this and say, well, you know, I don't see much pattern. The macroecology isn't jumping out at me. But there actually are two patterns that are very, very prevalent in the data. Most of the 101 data sets have a deficit of this pass-along triad. A beats B, B beats C, and we're waiting to see what happens between A and C. Many of them have a deficit of the pass-along triad type. And many or most of them have a deficit of cycles. In contrast, many or most have an excess, significant excess. Error bars don't go down to the 0 line. Significant excess of those double dominant types. There's a whole sort of interesting thing about how double dominants work. Excess of double dominants and transitives. So too few of the disorderly types, too many of the orderly types. So nature may seem disorderly. I thought I was done with the bad music, but I'm not. Nature may seem disorderly, so you might think with Greg Griffin of Bad Religion that nature is just a delirium of disorder. But we would argue, at least from the dominance world, that it may often be more orderly than it at first glance seems, as you see those animals sort of duking it out and trying to figure out a pattern. Take-homes. Random networks, I think, are a useful null model against which to compare observed data. Secondly, transitivity, this idea of counting the transitive relationships in the observed data and comparing them to the null expectation, may be a better measure of orderliness than this random imputation linearity model, which we argue forces in disorder. And thirdly, triad censuses show near universal tendencies for a deficit of disorder and an excess of order. Where am I on
No, you
time?
still got a minute and 40 seconds.
A minute and 40 seconds. Okay. So with that, I will. Okay. Do I have a minute for questions? Wow. Stunned so long. Okay, yeah, let's do that. Yeah, I'll answer questions about the bad music later.